This is week 7 of Applied Thermodynamics course. So till now this will be the last session on the IC engines, internal combustion engines. So we previously we saw how an internal combustion engine works and the various cycles which can be operated in an internal combustion cycle. like the Otto cycle, diesel or dual cycle. We saw some problems on those. So and we also saw the components of an internal combustion engines. So now we'll week we will focus mostly on the ignition part of it, and the performance. We'll do an exergy analysis of the internal combustion engine, and the heat transfer which happens in the internal combustion engine. So these are all what are the aspects which we'll be looking at this week. So I have prepared some problems and some MCQs on this. We'll start with those. So starting with MCQ. During the idling process, a petrol engine usually requires rich mixture. Answer A, true, or B, false. So rich mixture is when you have excess of fuel which is going in for a combustion process. So your stoichiometric for a fuel combustion to happen. So if your one mole requires some X amount of air, so that gives you complete combustion. A complete combustion with no residual fuel being present as a product. So that gives you stoichiometric reaction. So that is actually what you require, but in rich mixtures what you do is there is an excess of fuel which is present. So going with idling process. So idling process is nothing but when there is no load condition. So without load your engine is operating, so and your throttle is also clearly closed. So this you can say when you are at a signal, your car or bike is you have kept it on but you are not running. So this is in case of an idling process. So here there is no load, you are not putting any load for the vehicle to move or anything, but so here in this case your engine, the inlet throttle will be at its nearly closed position, but it will be such that open, such that the engine is running continuously. So due to this process of running, idling, so in this case what happens is the exhaust gases which is produced during the combustion, they remain in the combustion chamber, they are not fully taken away, and the amount of fresh charge that enters this less compared to the full throttling. So because the throttle is very nearly closed, so and full throttle case is when you are accelerating, so that's not happening. So the amount of fresh charge which is coming in is also less. So exhaust gas remains mixed with fresh charge admitted to the cylinder. So what happens is to start engine, you require much more fuel to overcome this dilution which is happening. So this can see so hence when you're just starting your vehicle, so this requires much more fuel for it to warm up and to give it initial push. So and there's also because of the dilution which is happening in the because of the exhaust gases, so this requires a much more richer fuel charge. So hence it's true. Next is by higher octane number of spark ignition fuel, it is meant that the fuel has dash higher heating value, B higher flash point, C lower volatility, D longer ignition delay. So here there are four criteria which is given, so which signifies to higher octane number. So higher heating value, which we have already seen, we have also saw some numericals on how to calculate higher heating value based on the reaction, and this we saw just the previous week. So we know that that doesn't signify any requirement on octane number, but B, if you see higher flash point is where you are getting a flash out of the vapors of the fuel, and lower volatility is the evaporation rate, and D is longer ignition delay. So that out of 4, the option D is a better is the correct one, because if you have a longer ignition delay, then the chance of knocking is very low, so you can avoid knocking. So you require a larger ignition delay, so higher octane number signifies this longer ignition delay. Next is a gas engine has a swept volume of 295 centimeter cube and clearance volume of 22 centimeter cube. Its volumetric efficiency is 0.82 and the mechanical efficiency is 0.91. So the volume of the mixture in centimeter cube inducted taken in per stroke is dash. So you have three values given: 235 centimeter cube, 242 centimeter cube and 245 centimeter cube. So what they have given is that it has a swept volume of 295 centimeter cube and clearance volume is given as 22 centimeter cube. So its volumetric efficiency is 0.82 and mechanical efficiency is 0.91. So the volume of the mixture taken. So it's a simple one. So there are many unrequired values given. So clearance volume is not required and mechanical efficiency is also not required to find out the volume of the actual mixture which has been taken. So if you see, volumetric efficiency is nothing but the actual volume taken verified by the swept volume. So theoretically, swept volume is the amount of the charge volume which is to be taken, but that doesn't happen. So this volumetric efficiency signifies that. So it is given as 0.82 and swept volume is already given as 295 centimeter cube. So the actual volume will be volumetric efficiency into swept volume, which is 0.82 into 295, which comes out to be 242 centimeter cube. So next is, which of the following statements are correct? Option A is higher compression ratio in diesel engine results in higher pressure. B, petrol engine works on Otto cycle. C, compression ratio for petrol engine varies from 6 to 10. And D, none of this. So if you see, out of this, all three are correct. So higher compression ratio, so in a diesel cycle, so if you have larger compression ratio, so your pressure will be higher. So that is known. When you are compressing, if you are compressing it to a smaller volume, correspondingly your pressure will increase. So option A is true. B is petrol engine works on Otto cycle. That is true. It's a spark ignition engine, and Otto cycle works in this. Petrol engine works as in a Otto cycle. And option C was also true. Petrol engine compression ratio will be in range of 6 to 10, and generally for diesel it will be around 10 to 14. So answer A, B, C, all three are true, are correct. So moving on to the next. Which of the following component is not an integral part with the SI engine? Option A, spark plug. Option B, ignition coil. Option C, fuel injector. Option D, carburetor. It is not a part of an ignition, it is a part of an spark ignition engine. So option will be option C, fuel injector. So the you see spark plug and ignition coil are for the ignition. So spark plug contains the ignition coil, so that creates the spark for the combustion to happen. And fuel injector and carburetor serves the purpose of giving you the charge for the combustion process. So fuel injector injects fuel. This is used in a diesel engine, or now we have gasoline injection also, but this fuel injector injects fuels into the combustion chamber, where only air is taken in and fuel is injected when a sufficient temperature and pressure is reached, and that creates a combustion. So that actually is not required for a spark ignition engine. And in a carburetor also plays a role of putting in fuel. So but this is a separate component where air comes in, and because of the pressure difference you have fuel which is mixed with the air, and it is taken to the piston cylinder arrangement. So carburetor is an integral part of an spark ignition engine, but fuel injector is not. So answer is option C. So next is, the octane number of isooctane is taken as dash. So octane number is defined based on isooctane, and the value is fixed at 100. So answer is option C, 100. So this is the reference. So octane number as a reference came because of isooctane. So that is marked as 100. So answer is option C, 100. Next is, the accumulation of carbon in a cylinder results in increase of dash. A, ignition timing. B, effective compression ratio. C, volumetric efficiency. And D, clearance volume. So answer will be option B, effective compression ratio. So if you see, when combustion happens, and as in the result you have carbon which is getting deposited on the cylinder head, so this effectively reduces your volume of the compressor. So if you see that effectively reduces your clearance volume. So you are now whatever fuel is there, you are compressing it to a smaller value compared to the previous clearance volume. So this reduction in volume is increasing the compression ratio of the engine. Hence answer is option B, effective compression ratio. Next is, in order to eliminate knocking in compression ignition engines, there should be dash. A, short delay period for the fuel. B, late auto ignition by the fuel. C, high self ignition temperature of fuel. D, low compression ratio for engine. So here if you see, the answer is option A, short delay period for the fuel. So you see, compression ignition engine, so knocking is basically your a combustion happening before your required required time. So if you're going back to how the engine works, so you're taking in the fuel, uh, there's a suction stroke, so if the piston comes down and the charge and air which are coming in, then you're compressing. So if for suppose the fuel is already injected, and before the piston has come to the top position, if the combustion starts happening, uh, then uh, the piston is still moving in the upward position, and your combustion is creating a pressure which is on the downward position, which is not required. So this creates unwanted vibration and sound and unwanted forces. So this is not desirable. So and to avoid this, what is done is basically given a short delay for the fuel, so that the combustion and this thing takes place correctly. So a late auto ignition by the fuel. So late auto ignition cannot happen. So B is ruled out. If you see C, high self ignition temperature of fuel. If high self ignition temperature is given, then your compression ratio required will be very high to reach that temperature, the self ignition temperature, which is generally not desirable. That's why you go for a spark ignition engine for fuel having high self ignition temperature. Then low compression ratio is also not desirable, as higher compression ratios will create higher temperature and pressure for fuel to self ignite. So B, C, D are not the correct options, but option A, short delay period for the fuel, is the correct option. The next question is, the spark plug is fired at 18 degrees from bottom top, 18 degrees before top dead center in an engine running at 1800 rpm. It takes 8 degrees of engine rotation to start combustion and get into flame propagation mode. The flame termination occurs at 12 degrees after top dead center. The bore diameter is 70 mm and the spark plug is 8 mm offset 2 from the center line of the cylinder. Calculate the effective flame speed. So what is given is the spark plug is there at the top of the cylinder arrangement, and before the crank when this is rotating, so suppose if the top dead center happens at 90 degrees, so from in the vertical position, so your cylinder is at the top position and the crank is at 90 degrees. So before 18 degrees before this rotation, your spark plug is initiated and the combustion takes place. So now 18 degrees you are initiating the spark plug, so that spark is created, and it takes again 8 degrees, so before 10 degrees before the top dead center the combustion is started and flame is propagating, and from 10 to 12 degrees, so 10 degrees before top dead center to 12 degrees after top dead center, that is 22 degrees of rotation is what takes for the flame to fully reach, and it goes into flame termination. So now what is given is the bore diameter is given as 70 mm and the spark plug is 8 mm offset from the center line. So it is 8 mm offset from center line, so it is not exactly at center. So calculate the effective flame speed. So we'll see how to solve this. So as I told, it takes 22 degrees for the flame to fully reach the cylinder walls to go into flame termination, because it once it touches the wall, there is no much charge for it to propagate again, so the flame will terminate at the walls. So so 22 degrees. So it's the spark plug is initiated at 18 degrees before, so it takes 8 degrees for it to start combustion. So it is now 10 degrees before top dead center, and it ends at 12 degrees after. So 12 degrees 10 degrees before to 12 degrees after. So if you see, it will be 22 degrees. So time it takes for this 22 degrees rotation is, for one revolution it will be 360 degrees. So for 360 degrees rotation in running at 1800 rpm, so 22 degree divided by 360 degree per revolution into 1800 divided by 60 revolution per second. So this gives you 0.00204 seconds. So this is the time it takes for the engine to rotate to 22 degrees. So maximum flame travel distance will be because the spark plug is at an offset, so maximum will be to the opposite side of where the spark plug is. So it will be half of the cylinder diameter plus the offset, so that will be the maximum distance to which the flame has to propagate. So you see the maximum flame travel distance will be bore by 2 plus offset. So bore is given as 70 mm, so 0.07 divided by 2 plus offset is 8 mm, so 0.008 gives you 0.043 meter. So effective flame speed will be velocity is distance by time, so 0.043 divided by 0.00204 gives you 21.078 meters per second. So that is close to 21 meters per second, and so answer is option B, 21. So it's a very simple problem. So we first found out how much time it takes for it to for the combustion to happen, so flame to propagate. So that we have found it to be 22 degrees. Then we found out how much time it takes for a 360 degree revolution. Then we divided it to find out how much it takes to for 22 degrees. Then we found out the maximum distance for which the flame has to travel, and then using these two we have found out the flame velocity or flame speed. Next is with increase in the speed of a SI engine, the crank angle required for flame propagation is affected. With increase in the speed of an SI engine, the crank angle required for flame propagation is affected. Option B, false. If the engine speed is doubled, so flame to traverse the combustion chamber is halved. So the time it requires for the flame to combust for combustion to happen is now reduced by half. So think this we'll go to the previous problem and see how to solve this. So if you see time, how I found out is from the crank angle divided by the speed. So now what happens is when you are running at double the speed, now the time required for combustion is also reduced. So the flame has to propagate at a higher speed. So if you see the speed is reduced and the time is also, the speed is doubled and the time is reduced. So effectively this crank angle, that will remain constant. So that will not change the where the spark is ignited. So where the crank angle has to be ignited, or the flame the crank angle is fixed. So irrespective of speed, whatever how much ever the speed is changed, the correspondingly the time is also will vary. So these two will negate each other, and your crank angle requirement will remain same for a spark ignition engine. So the answer is option B, false. So moving with the next question, compute the overall average heat transfer coefficient HO and heat flux Q double dash for a single cylinder engine with a 0.1 compute the overall average heat transfer coefficient HO and heat flux Q double dash for a single cylinder engine with a 0.1 meter bore and stroke, average combustion gas temperature of 1000 Kelvin, coolant temperature of 350 Kelvin, and fuel air flow rate of 2 into 10 power minus 3 kg per second. Assume K as 0.06 watt per meter Kelvin and mu as 20 into 10 power minus 6 Newton second per meter square. So with this, so the area of the piston is pi d square by 4. So the bore is given, you can find out area. The Reynolds number is given as your mass of air plus mass of fuel divided by area into diameter divided by mu. Reynolds number is a rho Vd by mu. So V is velocity, so you substituting, multiplying by area and dividing by area. So VA you can write it as Q, or volume flow rate. So rho into volume flow rate will be your mass flow. So mass divided by area into diameter divided by your viscosity. So this will come out to be 1274. So now the heat transfer coefficient is found using the correlation. Nusselt number equals 10.4 into Reynolds number raised to the power 0.75. So this is will be given in the question. So using this we can find substitute Reynolds number, and Nusselt number is nothing but H B by K. So HD by K. So 10.4 into K is given as 0.06 and diameter is known, and Reynolds number is 0.75. So this gives you 1330 watt per meter square Kelvin. So this is the heat transfer coefficient. Next, the heat flux from the cylinder to the coolant is therefore Q by A P which is H naught Tg minus Tc. So H naught we have already calculated 1330 into gas temperature is given as 1000 Kelvin and coolant temperature is 350. So this comes out to be 0.86 megawatt per meter square. So an inline 6 cylinder 6.6 liters 4-stroke cycle SI engine with multi-point port fuel injection operates at 3000 rpm with the volumetric efficiency of the intake manifold runners can be approximated as round pipes with an inside diameter of 4 cm. Inlet temperature to the manifold is 27 degrees Celsius. Calculate a average velocity and mass flow rate of air to each cylinder using inlet temperature to evaluate properties. So first we have an inline 6 cylinder engine. So 6 cylinders are in a straight line. So with total capacity of 6.6 liters, they are operating in a 4-stroke cycle as a spark ignition engine. So with multi-point port fuel injection, this operates at 3000 rpm with a volumetric efficiency of the intake manifold runner can be approximated as round pipe and that inside diameter is 4 cm. So inlet temperature to the manifold is 27 degrees Celsius. We need to find out average velocity and mass flow rate of air to each cylinder using inlet temperature to evaluate properties. Next is Reynolds number in runner to cylinder 1, which is 40 cm long. Temperature of the air entering cylinder 1. The runner wall temperature is constant at 67 degrees Celsius. So wall temperature needed for the runner to cylinder 3 such that the cylinder air inlet temperature is the same as that in cylinder 1. So runner length of cylinder 3 is 15 cm. So K is 0.02624. So with it, for one cylinder, your displacement volume will be 6.6 is the total capacity. So divide by 6, which gives you 1.1 liter. So with this, we can find out the mass flow rate. So mass will be rho Vd into volumetric efficiency into N. So rho is 1.181 into the displacement volume which we have calculated 0.0011 into volumetric efficiency is 0.89. I think that somehow got missed. With a volumetric efficiency of 0.89. So into speed is 3000 divide by 60 and divide by 2. So because it's in a 4-stroke engine, so one working stroke per 2 revolutions. So that comes out to be 0.0289 kg per second. So with that we can find out volume, which is mass by rho into A. So mass is 0.0289 divided by 1.181 into pi into 0.04 square divided by 4. This is the area of the runner. So this comes out to be 19.47 meter per second. Next is the Reynolds number. So Reynolds number is rho v d by mu. So substituting the values for the in the runner and the temperature given, pressure and temperature given for the runner. So Reynolds number comes out to be 49825. So next is Nusselt number. So Nusselt number will be putting a Didas Voltas equation 0.023, Reynolds number is to power 0.8 into Prandtl number is to power 0.4. So substituting the values, you get Nusselt number of 114.7. So H value is HD by K. Nusselt number is HD by K. So H value will be 114.7 into your K value 0.02624 divided by diameter 0.04. This comes out to be 75.2 watt per meter square Kelvin. So Q is nothing but HA dt, which is equal to mCp delta T. So H is 75.2 into area will be the perimeter of the runner. So pi into 0.04 to the first cylinder, it is given as 40 centimeter now. So 0.4 into the runner wall temperature is constant at 67 degrees Celsius and your temperature of air is 27. So 67 minus 27 is equals to the change in temperature. So 0.0289 into Cp, so 1005 into T0 minus 27, which is the inlet temperature. So T0 will be 32.2 degrees. So this is an approximate value of how to calculate T0, because the air value will also change here. Next is Q is HA dt, so equals mCp dt. So 75.2 into pi. Similarly, instead of 40 centimeter is 0.15 centimeter. So dt is equals 0.089 into 1005, and here it's given as wall temperature needed for the runner to cylinder 3 such that the cylinder air temperature is same as that of in the cylinder 1. So here we take temperature is 32.2 minus your inlet temperature is 27, so this comes up to 5.2. So the temperature difference which is required is 107. So the wall temperature in this case will be 134 degrees Celsius. So moving on to next question. During combustion, there is a momentary heat flux through the wall of the combustion chamber at a certain spot, so equal to gas temperature in the cylinder at this time is 3800 degree Rankine, and the convection heat transfer coefficient within the cylinder is coolant temperature is 185 degree Fahrenheit. So thermal conductivity of the 0.4 inch thick cast iron cylinder wall is 34 BTU per hour feet Rankine. So we'll move on to this question. So it's again here to just find out the heat transfer. So just like a similar problem. So Q, everything is given. We need to find out the wall temperature, and irrespective each wall 1 temperature and wall 2 temperature, and using that we can find out the Q will remain same, so we can find out the heat transfer coefficient on the coolant side. The next question is, two engines have cylinders that are geometrically the same in size and shape. The cylinders of engine A are surrounded with normal water jacket filled with water ethylene glycol solution. The cylinder of engine B are insulated, making this an adiabatic engine. Other than temperature, the engines are operated with the same steady state condition as much as possible. Which engine has higher volumetric efficiency and why? B. Which engine has higher thermal efficiency and why? C. Which engine has hotter exhaust and why? Which engine would be more difficult to lubricate and why? Which engine would be better SI engine and why? So we have 5 questions, and we have two identical engines, and one is cooled with a water in glycol solution, and other is an adiabatic engine. So what will happen is engine A will have higher volumetric efficiency compared to engine B, because engine B will have higher steady state operating temperature including cylinder wall temperature. So this will heat the incoming air to higher temperature, so which will reduce the air density and thus reduce volumetric efficiency. So what effectively is happening here is, so engine A, after combustion it is losing some of the heat to the water, and the water takes away that heat, and the engine itself is at a higher temperature but at a comparatively lower temperature to engine B. Why engine B is not losing any heat and it is insulated, so it itself is raising its temperature, and it's reaching its steady state by giving away some of the heat to the air. So the air which is coming in is heated to higher temperature compared to engine A. So engine B air is at higher temperature compared to engine A, and this higher temperature air reduces the density, so the effective mass of air which is coming in is reduced. So this causes a lower volumetric efficiency in engine B. Next is engine B will have higher thermal efficiency because heat losses will be minimum due to the insulated walls. And if you see, engine B will operate hotter than engine A, so Q in will be at higher temperature. So by thermodynamic law, the higher the temperature at which energy is used, the higher will be the efficiency of that use. So if you see, even in Carnot efficiency will be a W by Q1. So this you can write as T1 minus T2 divided by T1. So efficiency will be inversely proportional to the temperature, inlet temperature. So higher inlet temperature means the higher the negative term, so your efficiency will be higher. So engine B being at higher temperature, the heat which added is also of better use. So engine B would have to be a CI engine. Its wall would be too hot to operate as a SI engine, so the air fuel mixture would self-ignite during compression. So CI engines operate at higher compression ratio and thus have higher thermal efficiency. So engine B is better suited to be operated as a compression engine because of this case, or else if you have SI engine, so that will, because of this higher temperature, so there will be self-ignition, which you don't want. So engine B. Third is which engine has hotter exhaust. So engine B again will have hotter exhaust because all temperature engine B would be higher. So this will slightly reduce the thermal efficiency of engine B, but still in overall comparative wise it will give you a better efficiency. The higher temperature D is which engine would be more difficult to lubricate. So again it will be engine B because it's operating at higher temperature. There is a possibility of the lubricating oil getting cracked or thermal degradation of oil. So if you see in normally engines, when you try to change the oil, you will see kind of a black, the oil becoming black and the color will be not be, it will be a clear oil when you are you're putting in new oil to the engine, but when you take it out, the oil will be not in that state. It will be a kind of a black, so because of the thermal degradation which is happening to the oil. So the oil is a long chain molecule, so it cracks and there's a carbon particle which is being formed. So So this creates problem. So this you don't want. So this can be a problem in engine B because this is operating at higher temperature. So as told, so engine A would be better as a spark ignition engine, and engine B would be too hard to operate as a SI engine. So it will self ignite. So engine A is a better option for spark ignition engine, and engine B is a better option for a compression ignition engine. Next is a 6-cylinder SI engine with a total displacement of 1.86 liters operate at 2400 rpm using gasoline direct injection with 2 injections per cycle in each cylinder. The spark plug is fired at 19 degrees before top dead center, and there is an ignition delay of 0.0015 second before combustion is established. During combustion, there is a rich air-fuel mixture around the spark plug off, and a lean mixture is in the rest of the combustion chamber. With 2 injections per cycle. So we have 6-cylinder SI engine with a total displacement volume, so capacity of 1.86 liters. So each cylinder will be 1.86 divided by 6, and the operating speed is 2400 rpm, and it is operates as gasoline direct injection. So with 2 injections per cycle in each cylinder, the spark plug is fired at 19 degrees before top dead center, and there is an ignition delay of 0.0015 second before combustion is established. So and during combustion there is a rich air fuel mixture around the spark plug and lean mixture in the rest of the combustion chamber. The rich zone can be modeled as 2 cm diameter hemisphere around the spark plug with a flame speed of 32 meter per second. The lean zone then fills the rest of the combustion chamber to the outer edge of the bore and a flame speed of 19 meter per second. The engine has a compression ratio of 9.8, a stroke of 7.2 cm, and a connecting rod length of 13.3 cm with a spark plug at the center of the combustion chamber. Calculate crank angle position at the end of the combustion, piston speed at the end of the combustion, 3 volume in combustion chamber of 1 cylinder at the end of combustion. Option 1. So we'll see how to solve the first one. So crank angle position at the end of combustion. So your displacement volume is nothing but mc into pi by 4 into b square into s. So this will be 0.0186 meter cube. This is the total displacement volume. So 6 number of cylinders into pi by 4 into b square, and into stroke length is given as 720 m, 7.2 centimeter. So 0.072 meter. So from this we can find out the bore diameter as 7.4 centimeter. So now time for flame to reach outer edge of the fuel rich zone is, so distance divided by velocity. So velocity is given and the distance also is given as a hemisphere around the spark plug with the diameter 2 centimeter diameter. So to reach the edge is, it has to travel a radius of the hemisphere. So 0.02 divided by 2 divided by 32 meter per second. So this gives me 0.000313 second. So this is the time required to travel the fuel rich zone. So now to find out time to travel in the lean zone. So lean zone is now the bore diameter. So here the spark plug is at the center, so there is no offset here. Okay, so your time required for the lean zone will be the bore diameter minus the bore radius minus the rich zone distance. So your radius of the bore will be 0.074 divided by 2 minus again the distance for the rich zone, which is 0.02 divided by 2 divided by the velocity for the lean zone will be 19 meter per second. So this gives you 0.00142 second. So now the total time will be T is idle time plus, which is given, ignition delay. So ignition delay, its ignition delay is 0.0015 second. So ignition delay plus T1 plus T2. So this comes out to be 0.00323 second. So crank angle rotation during combustion is your speed, which is 2400 divided by 60. So this is revolution per second into 360 degree revolution divide into your time will give you the crank angle rotation. So this comes out to be 46.5 degrees. So position of crank angle at the end of combustion is, so 19 degree before top dead center. This is where the ignition was started, spark plug was fired. So after that plus 46.5, so it's basically 46.5 minus 19, so this gives 27.5 after top dead center. So this is where the crank angle will be at the end of combustion. So at 19 degrees before top dead center, so there will be ignition delay, and then there's a combustion in the fuel rich zone, and then the combustion in the lean rich zone. So this takes 46.5. So effectively, so 19 to 0 and then 0 to 27.5. So this is how much you are taking for the combustion. So the piston will be at the crank angle will be at 27.5 after top dead center. Next is this we have found the first one. So next is to find out the piston speed. So average piston speed is 2 times stroke into your speed. So 2 strokes per revolution into your stroke length, which is 0.072 meter per stroke, into revolution, which is 2400 divided by 60 revolution per second. So this comes out to be 5.76 meter per second. So this is the average piston speed. So crank offset is so it will be stroke length divided by 2. So this comes out to be 3.6. So piston speed at the end of combustion will be, you can find out R, which is R by A. So connecting rod length is 13.3 and crank offset is 3.6. So this comes out to be 3.69. So your piston speed by average piston speed is pi by 2 sin theta into 1 plus cos theta divided by root of r square minus sine square theta. So we have found out the crank angle at the end of combustion, so that is 27.5. So pi by 2 sine 27.5 into 1 plus substituting theta value and r square values. So this comes out to be 0.9. So your piston speed is 0.9 times the average piston speed, which comes out to be 5.18 meter per second. So this is the piston speed at the end of combustion. Next is to find out the combustion chamber volume at the end of combustion. So for this we will find out the displacement volume first. The displacement volume for one cylinder is 1.86 divided by 6, which is 0.31 liters or 310 centimeter cube. So clearance volume for one cylinder will be can get it from the compression ratio. So RC is your total volume divided by the clearance volume, which is 9.8. So from this the clearance volume is 35.2 centimeter cube. So the combustion chamber volume at the end of combustion is 1 plus V by Vc is 1 plus half of the compression ratio Rc minus 1 into R plus 1 minus cos theta minus root of R square minus sine square theta. So substituting the compression ratio and the R and theta values will give you volume of 57 centimeter cube. So this is the volume at the end of combustion. So moving on with the next question. A small airplane has a modified supercharged 2.4 liter spark ignition engine equipped with variable compression ratio. The Otto cycle engine is operated in two different modes: high load takeoff and low load cruising, with the following conditions. Calculate 1. Indicated thermal efficiency at takeoff and at cruising. 2. Rate of fuel flow into engine at takeoff and at cruising. 3. Indicated power at takeoff and at cruising. 4. Indicated specific fuel consumption at takeoff and at cruising. So this is the engine condition, operating condition during takeoff and cruising. So engine speed is 3600 rpm and during cruising is 2200 rpm, and compression ratio is 8:1, and compression ratio during cruising is 14:1. And volumetric efficiency is also given as 120% during takeoff and 88% in cruising. And fuel is in stoichiometric ratio, and in cruising it is in air fuel ratio is 22:1. And combustion efficiency is given as 97% during takeoff and cruising as 99%. So with this we will see how to calculate. So indicated thermal efficiency can be calculated as, so with the SI engine formula. So efficiency formula is 1 minus 1 by RC raised to power gamma minus 1. So during takeoff the compression ratio is given as 8. So 1 minus 1 by 8 raised to power gamma we are taking as 1.35. So 1.35 minus 1 comes out to be 51.7%. So So that is indicated thermal efficiency during takeoff. And similarly, for cruising, your compression ratio is given as 14. So 1 minus 1 by 14 raised to power 1.35 minus 1, which comes out to be 0.603 or 60.3% at cruising. So if you see, during cruising you have much more efficiency. Next is mass flow rate of air into the engine is volumetric efficiency into rho into the displacement volume into your speed. So your volumetric during takeoff, your volumetric efficiency is 120%, so 1.2 into your density is 1.181 into displacement volume is 0.0024 meter cube, because your is given as 2.4 liter, so 2.4 into 10 power minus 3 into speed is during takeoff is 3600 divided by 60, since it's a SI engine, so 4 stroke, so divide by 2, so this comes out to be 0.1020 kg per second at takeoff. And similarly we can calculate for cruising. So cruising volumetric efficiency is for 80%, so 0.88 into density 1.181 into again your displacement volume into speed divided by 2, so this comes out to be 0.0457 kg per second, which is at cruising. So mass flow rate of fuel into engine is, so mass flow rate m dot A divided by air fuel ratio, so air fuel ratio is 14.6. The stoichiometric gasoline air fuel ratio is 14.6. So m dot F is 0.00699 kg per second at takeoff, and mass of fuel at cruising is, so 0.0457 mass of air divided by air fuel ratio, so this comes out to be 0.00208 kg per second at cruising. So cruising is nothing but your vehicle running at a constant speed. So 3 is indicated power. So indicated power is nothing but your thermal efficiency into mass of fuel into the combustion calorific value into combustion efficiency. So indicated power is your thermal efficiency, so 0.517 for takeoff into your mass of fuel which you are taking 0.00699 into your calorific value 43,000 kilojoule per kg into combustion efficiency of 0.97. This gives you 151 kilowatt at takeoff. Similarly for cruising, you know thermal efficiency is 0.603 into your mass of fuel which is 0.00208 into your CV into combustion efficiency of 0.99, gives you 53 kilowatt. Next is your indicated specific fuel consumption, which is nothing but mass of fuel divided by your work. Here in this case indicated, so you will use indicated work. So this comes out to be 167 grams per kilowatt hour during takeoff and 141 gram per kilowatt hour during cruising. So next is an SI engine operating at 12,000 rpm has a 10.2 centimeter bore. The spark plug offset by 6 mm from center. The spark plug is fired at 20 degrees before top dead center. It takes 6.5 degrees of engine rotation for combustion to develop and get into flame propagation mode, where the average flame speed is 15.8 meter per second. Calculate time of one combustion process after flame has developed. that is time for flame front to reach the furthest cylinder wall, and crank angle quotient at the end of combustion. So first is flame travel distance is nothing but 4 by 2 plus offset, which you have seen. So the distance is 0.057 meter. So time is the distance divided by the flame velocity, so which comes out to be 0.0036 seconds. So that is the total time which requires for the combustion process. Next is, so you say the combustion starts at 13.5 degrees before top dead center. So time of combustion in degree of rotation, so the time into your engine speed, so 1200 divided by 60 into 360 hours, so this gives you 25.9 degrees. So crank quotient which will be at the end of combustion will be, so 25.9 minus 13.5 gives you 12.4. So the combustion will end after 12.4 degrees top dead center. So we want to next question. It is desired that flame termination be at the same crank angle position when the speed of the engine increased by 2000 rpm. So in this range, flame development takes the same amount of real time, and flame speed is related to engine speed as V is 0.92 n. Calculate flame speed at 2000 rpm, crank angle position when the crank spark plug should be fired, crank angle position when flame propagation starts. So velocity now, flame velocity now is 0.92 into 2000. So previously it was running at 12,000 rpm, and the flame velocity is given as 15.8 meter per second. So velocity for mu will be 24.23 meter per second. So the real time of combustion development will be T is 6.5 degrees. So saying it is that flame termination be at the same crank angle position. The speed of engine in problem 1 is increased to 2000 rpm. So flame development takes the same amount of real time, and flame speed is related to engine speed. So the flame development takes the same amount of time, and flame termination also happens at the same crank angle. So flame development takes 6.5 degrees of engine rotation. So the time taken for the flame development is 6.5 degrees divided by 360 into the speed for the previous case. So it is 1200 rpm. So that comes out to be 0.0090 second. So time of combustion at 2000 rpm is T is d by velocity. So your distance is again same, there is no change. So 0.057 meter divided by velocity is 24.23. This comes out to be 0.00235 second. So total time of ignition and combustion will be 0.00325 second. So total time in degrees of engine rotation will be, substituting this with the speed, will get 39 degrees. So for combustion to end at 12.4 after top dead center, the spark plug must be fired 26.6 degrees before top dead center. So previously in the problem, if you see, the spark plug is fired at 20 degrees before top dead center, but when the speed is increased to 2000 rpm, it should be fired 26.6 degrees before top dead center. So now engine rotation during combustion, crank rail position when flame propagation starts. So engine rotation during combustion will be the combustion time, and converting that to the degrees of rotation, it will come out to be 28.2 degrees. So with this, we know that it ends at 12.4 degrees. So 28.2 minus 12.4, so this comes out to be 15.8 degrees before top dead center. So this is where the combustion will start. So this is the final problem which I have prepared for today. We'll do an exergy balance of an Otto cycle. So consider an Otto cycle as shown in figure that has compression ratio of 6, compression efficiency of 85% and an expansion efficiency of 90%. At the beginning of compression process, air is at 101.3 kilopascal and 25 degrees Celsius, and the maximum temperature and pressure that occur during the cycle are Pmax 1300 Kelvin and Pmax of 4 megapascal. Accounting for the variation of specific heats of air with temperature, assuming Ts is 2000 Kelvin and T0 as 293 Kelvin, find the net work and heat transfer to the air during the heat addition process. B. Calculate the exergy destruction during the expansion process, and C. Find the energy and exergy efficiencies. So we have an Otto cycle, and compression expansion efficiency is given, and at the start the pressure and temperature is also given. So they are also given the maximum temperature and the pressure. So accounting for variation of specific heat of air where temperature assuming the source temperature is 2000 Kelvin and T0 as 293 Kelvin. So find the net work and the heat transferred to the air during the heat addition process, and calculate the exergy destruction during the expansion process. Find the energy and exergy efficiency. So we'll see how to solve this problem. So this is how the process looks. So 1 to 2 is a reversible adiabatic process, but now it's not. So there's efficiency is given. So it goes from 1 to 2, then a constant volume heat addition, then an isentropic process. So which expansion given. So it will follow 3 to 4, and then constant pressure, constant volume heat rejection. So P1 and T1 is given, which is 101.3 kilopascal and 298 Kelvin. So with this, at this point you can find out from a table. So since this they are saying that variation of specific heat is it has to be considered, so we'll take data from the air table, air standard table. So for this pressure and temperature, you can find out internal energy is 214.3 kilojoule per kg, and your specific volume is 0.85 meter cube per kg. So this being isentropic process, we can estimate the temperature at the end of the process 2s. So 2s will be T1 into V1 by V2 raised to power gamma minus 1. Since the compression ratio is 6, so substituting that, and the inlet temperature is close to 300, so this will be 614.3 Kelvin. with the compression, if compression efficiency given, so which will be T2s minus T1 divided by T2 minus T1, which is 85%. So with this we can find out the actual temperature T2, which is 669.8 Kelvin. So corresponding to this temperature and the specific volume V2, which is 6 times of V1. Here U2 will be 489 kilojoule per kg, and we can find out pressure at state 2. So P2 by P1 raised to power gamma minus 1 by gamma, which is T2s by T1. So P2 will be 1274 kilopascal. So similarly we can find out so the maximum pressure and maximum temperature is given. So that is state 3, which is 1300 Kelvin and 4 megapascal. So with a similar process we can estimate the state 4. So state 4 temperature is 701.4 Kelvin using the isentropic temperature and the expansion efficiency. So we know T4. So Q in is nothing but CV T3 minus T2, which is 0.718 into 1300 minus 669.8 is 452.5 kilojoule per kg, and W net is Q2 minus Q1. So CV T3 minus T4 minus T2 minus T1 or 0.718. In substituting all temperature we can get 164.3 kilojoule per kg. So this we can use to find out using a constant CV values, or else we can find out each individual internal energy values, and we can get the difference to find out the Q in value and Q out value. So to find the exergy destruction during isentropic expansion, so EX3 is nothing but CV T3 minus T0, which is the ambient temperature, minus T0 S3 minus S0. So this will come out to be 570.1 kilojoule per kg, and similarly EX4 is CV T4 minus T0 minus T0 S4 minus S0, which is 133.8 kilojoule per kg. So U3 is U4 plus W0. So W out will be 429.8 kilojoule per kg. So exergy destroyed here is nothing but doing exergy balance. So EX3 which is coming in equals the terms which are going out. So EX4 plus W out plus the exergy destroyed. So exergy destroyed will come out to be 6.5 kilojoule per kg. So now we can calculate the exergy efficiency and energy efficiency. So the net work which is generated is 164.3 kilojoule per kg, and the heat added is 452.5, which we have calculated. So the overall efficiency is 36.31%, and exergy efficiency is nothing but your net work divided by the ideal work, which maximum work which you can generate. So that you can generate using a Carnot cycle. So Q in into 1 minus T0 by Ts. Source temperature is given as 2000 Kelvin. So 164.3 divided by 452.5 into 1 minus 293 divided by 2000. So this comes out to be 42.55%. So this basically says that if the ideal Carnot cycle can give you 100 kilowatts, this will give you 42.55 kilowatts. So that's the exergy efficiency. So with this I have finished what I prepared for today, and also we have finished for IC engines. So next we will move to gas power cycles or Brayton cycles next week. Thank you.